Welcome to today's Explainer. Sometimes meteorology feels less like a science and more like the plot of a Hollywood disaster movie. But what we're looking at today is happening right in front of us, in the real world. We're diving into the incredibly rare, totally chaotic, and honestly terrifyingly powerful atmospheric science behind a double-feature storm system. Right now, two massive, distinct spinning systems, tropical storms Higos and Mekkhala, are cruising along Japan's Pacific coast at the exact same time. We're going to break down the exact science of how this happens, why it happens, and what it actually means for the people right in their path. Let's get into it.
Okay, let's dive into this. Two. Just two. The reality of that number is literally awe-inspiring. We are talking about two distinct, fully formed tropical storms bearing down on a single country at the exact same time. I mean, it's hard enough for a region to prep for just one cyclone, right? But when the atmospheric steering currents line up perfectly to send a binary storm system toward a single coastline, the complexity of that threat just multiplies exponentially. To really understand how we end up with two storms knocking on the exact same door at once, we need to pop the hood and look at the atmosphere's underlying machinery.
Section 1. Atmospheric ingredients. Let's look at the perfect recipe. So consider this our atmospheric crime scene investigation. The whole thing starts right here, with our main incubator, the monsoon trough. If you look at the Western Pacific, you'll constantly find this massive, elongated area of low pressure. You can basically think of it as a super fertile breeding ground for severe weather. Now, when this trough gets particularly wide and really active, it doesn't just birth one storm. Instead, multiple pockets of spinning air, which meteorologists call vorticity, can actually develop right alongside each other, in super close proximity. And as it turns out, that is exactly how our current twin threats, Higos and Mekkhala, were brought into the world.
We can really trace the sequential buildup of this crazy anomaly in three distinct steps. Step 1 is that monsoon trough we just talked about, incubating those twin pockets of spinning air. But storms don't just wander aimlessly, do they? They need to be steered. And that brings us to Step 2, the Subtropical Ridge, which basically serves as the highway. Finally, as these systems approach land, they hit Step 3, the Baiu. That's Japan's seasonal rain front, and it acts as the ultimate amplifier for the impending disaster. Let's take a closer look at that highway.
And this brilliantly illustrates how tropical cyclones actually move. They don't drive themselves. They're essentially pushed around by massive global winds. Just south and east of Japan, there's this huge, semi-permanent high-pressure system called the Subtropical Ridge, or the Pacific High. The winds flow clockwise right around the edge of this ridge, acting literally like a giant conveyor belt, sweeping any storms that form along its perimeter straight toward mainland Japan. So, if two storms form in that trough and hop onto this highway one right after the other, well, they're forced onto the exact same track.
Which brings us to the amplifier just waiting near the coast. Japan has this seasonal rain front called the Baiu, and right now this frontal system is completely stalled over the region. When Higos and Mekkhala roll up, this stalled front acts like a gigantic atmospheric sponge. It's actively absorbing massive amounts of moisture from both of these storms simultaneously. And the result of that? Record-breaking, absolutely catastrophic downpours that start flooding the country well before the actual centers of the storms even brush past the landmass.
Section 2. The Fujiwhara Effect, the orbital storm dance.
So, when two massive cyclones ride the exact same atmospheric highway and close the distance to roughly 1,000 to 1,400 kilometers apart, that's about 600 to 850 miles for us, it prompts a pretty blunt question. Do they just cancel each other out? Do they kind of break each other apart and save the mainland from disaster? I mean, it's a really comforting thought, isn't it? Let's look at the reality.
Now, what's really interesting about this slide is how it contrasts our intuition with reality. We intuitively want the atmosphere to just act like simple math. We desperately want one typhoon minus another typhoon to equal zero threat. It's a lovely thought, but, the atmosphere totally doesn't care about our math. Instead of cleanly zeroing out, these storms begin an intense, highly unpredictable orbital dance. The mechanics of this dance are incredibly complex, but they generally end up going down one of three paths. Under this phenomenon, the Fujiwhara effect, we basically see three actual scenarios play out. First up is mutual orbit. This is where the two storms begin to literally pivot around a common center of gravity situated right between them. They essentially swing each other around, which radically alters their paths and makes track forecasting a complete nightmare for meteorologists. The second scenario is absorption, and the third is wind shear dissipation. Both of these latter two have absolutely severe consequences for anyone caught in their path. Let's examine absorption first. This scenario is often vividly and terrifyingly referred to as the cannibal storm. If one of the two storms is significantly larger or packing more power than the other, it won't just politely orbit its weaker sibling. No, it will actively eat it. The larger storm's massive circulation will literally pull the smaller cyclone's moisture and energy straight into itself. So, far from canceling out, the surviving cannibal storm sometimes grows even larger, much wider, and way more structurally chaotic as it comes bearing down on the coast.
But what about that third scenario, wind shear dissipation? Well, this happens when the massive spinning outflow of air, exhausting out of the top of the stronger storm, acts as a literal wall of hostile wind shear against the weaker one. This shear can structurally shred the weaker storm apart, downgrading it to a mere tropical depression. So the crucial point is this: even when a storm is structurally destroyed, the energy doesn't just vanish. The shredded storm's massive towering column of moisture is still sitting right there in the atmosphere, and it just gets released as an extreme, highly concentrated deluge of rain over whatever landmass happens to be sitting directly underneath it.
Section 3. The global perspective. Let's move to and see how this builds by looking at worldwide storm stats. We've zoomed in heavily on the specific mechanics threatening Japan right now. But zooming out from Japan for a second, the Western North Pacific Basin is the undisputed global hotspot for this kind of extreme weather. Globally, this single basin is home to nearly 1/3 of all tropical cyclone activity on Earth. Why? Well, because the ocean waters here are incredibly deep, and more importantly, they are exceptionally warm. This provides essentially endless fuel for these spinning giants to form and sustain themselves.
And because this basin is just so incredibly active, binary typhoon configurations, two storms happening at the exact same time, are not some once-in-a-lifetime freak event here. In fact, in the western North Pacific alone, a binary storm setup occurs roughly 1.5 times per year on average. It is a regular, fully expected feature of their storm season. But wild as it sounds, the atmosphere doesn't always stop at 2.
During the absolute peak months of the typhoon season, particularly in August and September, the Western Pacific essentially goes into overdrive. It's actually not all that unusual to see 3 active storms simultaneously churning out there in the ocean. And in incredibly rare but fully documented instances, satellite imagery has actually captured 4 or even 5 active tropical cyclones stretched out across the Pacific at the exact same time. It is just a breathtaking display of atmospheric power.
Section 4. The real-world danger. The immediate coastal threat. Now, looking at satellite images of 5 storms is scientifically fascinating for sure, but for the actual people living on the coastlines dealing with Higos and Mekkhala today, it is very much a matter of life and death, because these 2 storms are moving in tandem along the coast, and because that Baiu rain front is acting like a giant sponge, the resulting moisture combination is just unprecedented. It amplifies the flood and landslide risks significantly. Even if the Fujiwhara Effect kicks in and Higos structurally breaks down Mekkhala via wind shear, the danger absolutely has not passed. The structural wind threat might diminish, sure, but the massive combined water volume from both systems remains. Residents simply must remain hypervigilant.
Which leaves us with a rather unsettling reality to consider. We so often judge a storm's danger by its wind speed, right? We breathe this huge sigh of relief when it gets downgraded or shredded by a larger companion storm. But as we've seen with the atmospheric science of Japan's binary storms, the water remains. So it forces us to ask, if a destroyed storm still drops a deadly deluge, are we ever truly safe from the remnants? It's a sobering reminder that long after the spinning winds stop, the terrifying reality of binary storms continues to fall right out of the sky. Thank you so much for joining me for this explainer, and keep looking up.